Hello everyone, welcome to the SheshKamal Academy. We have started the lecture series for fluid mechanics for preparation of various competitive examinations. So I have already uploaded 2 lectures on the unit 1, which is the basics of fluid mechanics, that is property of fluid mechanics and its a classification. The link for those videos I will be putting in the description box. Today we are going for the numerical based on that topic. So I have collected the numericals or questions that has been asked in the GATE and IES examination. So the collection I have made from the year of 1998 to 2022. So let's start for the questions. Now the first question is the on surface tension. So the surface tension is a phenomenon. It is purely because of cohesion. So option B is the correct answer. Then second question is the Newton's law of viscosity depends upon. The correct answer is option C. Option C, because the Newton's law of viscosity states that the shear stress is directly proportional to du by dy, and this du by dy is nothing but the rate of strain, and this tau is the shear stress. Option C is the correct answer. Now next, the shear stress developed in the lubricating oil of viscosity 9.81 poise. So viscosity is given, filled between the two parallel plates 1 centimeter apart and moving with relative velocity 2 meter per second. So we have to find out the shear stress. So the formula for shear stress is tau is equal to mu into du by dy. So the value of mu is given in poise, convert it into SI unit. So poise is nothing but Celsius unit. So 1 poise is 1 by 10 Newton second per meter square. So mu in SI unit will become 0.981. Okay, Newton second per meter square. And y is 1 centimeter. So it is nothing but 0.01 meter. So put the values. So it is 0.981 viscosity into velocity is 2 meter per second divided by 0.01. It comes out to be 196.2 Newton per meter square. So option B is the correct answer. Now fourth one, the capillary rise at 20 degrees Celsius in a clean glass tube of 1 mm diameter containing a water is approximately. So we have to find out the capillary rise. That means how much height is increased as you dip the glass tube of diameter 1 mm inside the water. Okay, so here actually the formula just I will write here. So H is 4 sigma cos theta divided by rho g into d. The value of theta is 0 for the glass and water interface. So cos theta is 0. So cos 0 is 1. Then the sigma value. Okay, sigma is surface tension. Now you have to remember the value of surface tension at 20 degrees Celsius. So it is 0.0736 Newton per meter. The value of H 4 into 0.0736 cos theta or cos 0 is 1. Rho is 1000 into 9.81 into diameter. Diameter of tube is 1 mm. So 1 into 10 raised to power minus 3 meter. So if you calculate this value, it comes out to be 30 mm. So first you get it in meter. You have to convert it into mm because all options are given in mm. So option D is the correct answer, 30 mm. Now next, you have to match the list 1 with list 2. So list 1 contains the type of fluid and list 2 is the variation of shear stress. Okay. So now see, A is the ideal fluid. So for ideal fluid, the shear stress is 0. If you see on the list 2, the fourth one is the shear stress is 0. Option, so A matches with the 4. Newtonian fluid is a fluid where the shear stress is varies linearly with the rate of strain. Okay, so if you observe in a list 2, B matches with the 1. Now non-Newtonian fluid, the shear stress does not vary linearly with the rate of strain. So if you see in the list 2, it matches with number 2. Now Bingham plastic fluid. So 4, 1 all are completed. So remaining is 3. So the D matches with 3. Answer will be A4, B1, C2, D3. Okay, so see the answer. Now next is related to assertion and reason. Assertion says in general, viscosity of liquid increases and in gases, it decreases with rising temperature. So viscosity of liquid increases and it decreases for gases with rising temperature. So assertion is a false because viscosity, that is mu of liquid, decreases as temperature increases, and for mu of gas increases as temperature in assertion is false. It is false. Now the reason, so viscosity is caused by the intermolecular force of cohesion and due to transfer of molecular momentum between the fluid layer. This up to this the statement is correct. Now, of which in liquid the former and in gases the latter contributes the major part. So one more thing, I have already discussed you that the viscosity in the liquid causes because of change in cohesive forces, and for the gases, as you increase the temperature, there is a molecular momentum transfer. Okay, molecular momentum transfer. So reason is correct, but it is not the correct explanation of A assertion, because assertion is already false. Okay, so option D is the correct answer. Option D is the correct answer, because only in option D A is said as a false and R is a true. Option D is the correct option. Okay, next, match the list 1, which is rheological equation, with the list 2 type of liquid and select the correct answer. So list 1 contains rheological equation and list 2 contains the type of fluid. So rheological equation, so generalized rheological equation is tau is equal to mu 0 plus mu, okay, mu 0 plus mu du by dy raised to power n. So this is generalized rheological equation. Now by varying the value of mu and n, okay, we have to identify the equation for which fluid it is. Option A, where the option A, if you put n is equal to 1, it is simply tau is equal to mu du by dy. Okay, and this is nothing but the statements of Newton's law. So it is valid for the Newtonian fluid. So this A matches with 3. A matches with 3. Then B, tau is equal to u du by dy raised to power n, and value of n is less than 1, is for the pseudoplastic fluid. So B matches with 4. Then tau is equal to mu du by dy raised to power n and n greater than 1. So it is matches with the dilatant fluid. So this is for dilatant fluid. And then tau is equal to mu 0 u du by dy raised to power n, and where n is equal to 1. So this contains here a mu 0. It is nothing but the initial stress, and this rheological equation is valid for the Bingham plastic fluid. So option, the correct answer is A3, B4, C2 and D1. Next, the oil of specific gravity 0.9 has a viscosity of 0.28 Stoke at 38 degrees Celsius. What will be the its viscosity? That is mu, you have to find out. And formula for mu is equal to rho into nu. Density is not given directly, specific gravity is given, and from specific gravity you can find out the density. So value of density is 900 into nu. Kinematic viscosity is 0.28. It is in Stoke, so convert it into meter square per second. So multiply by 10 raised to power minus 4. Came out as a 0.0252. So option C is the correct answer. Now how to find out the density from the specific gravity? So it is the specific gravity is nothing but the property of fluid actually. So it is denoted by S, and it is nothing but density of, that is rho of any liquid to the density of standard liquid. The standard liquid we always considered as a water. So as you given as S is 9, so rho of liquid divided by 1000. So you will get rho of liquid is equal to 0.9 into 1000. So it is 900. And now nu. So I already told you that 1 Stoke is equal to 10 raised to power minus 4 meter square per second. Meter square per second. So 1 Stoke is equal to 10 raised to power minus 4 meter square per second. So now 0.28 Stoke is equal to 0.28 into 10 raised to power minus 4 meter square per second. Okay, so this is the conversion from CGS unit to SI unit. Then question number 8 is, when the pressure on a given mass of liquid is increased from 3 megapascal to 3.5 megapascal, the density of liquid increases from 500 kg per meter cube to 501 kg per meter cube. What is the average value of bulk modulus of a liquid over the given pressure range? So we have to find out the value of K, and the formula for K is change in pressure divided by volumetric strain, that is dV by V. It is also can be written as change in pressure divided by change in density to the original density. So here the density is given, so we have to use this relation for calculating this value of bulk modulus. So K is equal to change in pressure. So change in pressure is 3.5 minus 3. It is in megapascal. So all the answers are in megapascal. So just keep it in megapascal. Then change in density divided by density. Change in density is 501 minus 500 divided by 500. So if you solve this, you will get the value of 250 megapascal. So correct answer is option D. Now the next question is, if the relationship between the shear stress tau and the rate of shear strain as tau is equal to u du by dy raised to power n, then the fluid with exponent n greater than 1 is known as which of the following? The rheological equation is given, that is tau is equal to mu into du by dy raised to power n. Okay, and the value of n is given greater than 1. So if you plot this on du by dy versus tau, okay, so the value for n greater than 1 and with no initial state, so obviously the graph will start from the origin. So the nature of the graph will like this, and this graph is nothing but for dilatant fluid. So option B is the correct option. Now next, what is the dimension of kinematic viscosity of a fluid? So unit of kinematic viscosity, that is nu, is meter square per second. So its dimension will be L square t to the power minus 1. Option B is the correct answer. Now the assertion is blood is a Newtonian fluid, and the reason is the rate of strain varies non-linearly with the shear stress for the blood. Okay, so assertion, it said that the blood is a Newtonian fluid, but actually blood is not Newtonian fluid. So this assertion is wrong. Okay, so blood is actually the pseudoplastic fluid. Okay, so this assertion is wrong. Now the reason, the rate of shear strain varies non-linearly with the shear stress for the fluid. So the reason is correct, but actually it is not the correct explanation of A, because assertion is already wrong. The reason could not be the correct explanation for A. Option D is the correct answer for this given question. Here I have already explained you the things related to pseudoplastic fluid. So you can see on the screen. So the blood, pseudoplastic fluid, and where the viscosity decreases with the increase in shear stress. So option D is the correct answer. Now in an experiment, the following shear stress time rate of shear strain value are obtained for the fluid. So the first row contains the time rate of shear strain, and second is the shear stress. Okay, so this time rate of shear strain is nothing but du by dy. Okay, du by dy, and this is tau. So if you plot the graph, so the graph will look like this, and this is nothing but the dilatant fluid. Okay, so option D is the correct answer. Now moving ahead, what is the unit of dynamic viscosity of fluid term as a poise? So CGS unit of dynamic viscosity is nothing but the poise, and the CGS unit for dynamic viscosity is dyne second per centimeter square, and it is also termed as a poise. So option 3 is the correct answer. Now next, what is the pressure difference between inside and outside the droplet of water? So from the surface tension phenomenon, actually the relation is came out for pressure P is equal to 4 sigma by D for water droplet. So this is the formula for pressure difference inside and outside the water droplet. So option B is the correct answer. Now what is the pressure inside a soap bubble over the atmospheric pressure? And when you talk of the soap bubble, so the relation between P and sigma is P is equal to 8 sigma by D. So just put the value. So 8 into sigma, value of sigma is 0.1 divided by 2, diameter is 2 centimeter, convert it into meter, 40 Newton per meter square. So option C is the correct answer. Next, which of the following is correct? The capillary rise or depression in a small diameter tube is. Okay, so I will write the formula for capillary rise is H is equal to 4 sigma cos theta divided by rho z d. The value of a rise in capillary, H is directly proportional to sigma, is inversely proportional to z into D as well as density. So just find out the correct options. So option A is directly proportional to specific weight of the fluid. So there is no specific weight parameter for capillary rise. Inversely proportional to the surface tension. It is actually wrong. It is directly proportional. Then inversely proportional to the diameter. So here you can see it is H is inversely proportional to the diameter. So this is the correct answer. So option C is the correct answer. Now next, what is the capillary rise in a narrow two-dimensional slit of width W? So the formula for capillary rise or fall in a tube, we have seen the formula, that is H is equal to 4 sigma cos theta divided by rho GD. Okay. So when there is a narrow slit, so the formula, just to remember it, H is equal to 2 sigma cos theta divided by rho GD. So just you have to find out the how much times it is the capillary rise inside the tube. So it is half of, okay, just if you divide these H or do H by 2, so you will get the value of rise of capillary for slit. So option A is the correct answer. Then for the pseudoplastic fluid, for which option A is dynamic viscosity decreases as the rate of shear increases. Option B is Newton's law of viscosity holds good. Option C is dynamic viscosity increases as the rate of shear increases. Dynamic viscosity increases with the time for which the shearing force are applied. So option A is the correct answer, because the density decreases with the increasing shear stress, okay, or rate of shear. And the pseudoplastic fluid is also called as a shear thinning fluid because the viscosity decreases with increasing shear stress. The next, if the angle of contact of a drop of liquid is acute, then option A is adhesion is more than cohesion. B, cohesion is more than adhesion. Option C is cohesion is equal to adhesion. Option D is adhesion and cohesion have no bearing with angle of contact. So option A will be the correct answer, because when there is an acute angle, so in that case there is a rise of a capillary, okay, and the rise of capillary is possible when adhesion dominates the cohesion. The option A is the correct answer. Adhesion is more than the cohesion. Match the list with list 1 with list 2. So the phenomenon of capillary is because of surface tension. Okay, so option 4 from the list 2. Vapor pressure, it is for 1, is responsible for cavitation. Viscosity is about the shear forces, and the specific gravity is related to density. Option D is the correct answer. Now with the increase in pressure, the bulk modulus of elasticity. So obviously the bulk modulus will increases with the increase in pressure. So option A is the correct answer. Next question is, in an experiment to determine the rheological behavior of a material, the observed relation between shear stress tau and the rate of shear strain is du is equal to tau 0 plus c du by dy raised to power n. Then the fluid is. So here if you observe, the value of n is less than 1, okay, less than 1, and there is also a initial shear stress. The rheological equation is applicable to thixotropic, or it is a representation of thixotropic fluid. So option A is the correct answer. Now next, the unit of following parameter is meter square per second. So option are given as a thermal diffusivity, kinematic viscosity, mass diffusivity, and dynamic viscosity. Actually, the question is like that: the which of the following parameter is not having a unit of meter square per second? So obviously, the dynamic viscosity is not having the unit of meter square per second. So option D is the correct answer, because its unit is Newton second per meter square. So option D is the correct answer. Next, Newton's law of viscosity relates the shear stress to rate of shear strain, or rate of deformation, or rate of angular deformation, and it is also called as the velocity gradient. So option, say, rate of shear deformation to shear stress. So option B is the correct answer. Moving ahead, match list 1 with the list 2. List 1 contains the fluid and list 2 contains the viscosity that fluid is. So when you say ideal fluid, so obviously the description for ideal fluid, it has no viscosity, the mu value is 0, okay. Then Newtonian fluid, so B is a Newtonian fluid, so it is related to du by dy, so from the statements of Newton's law of viscosity. Option C, it is inviscid, means again the mu is 0. Then option D is a real fluid. So obviously the mu value is not equal to 0. So if you observe this, so A ideal fluid has 0 viscosity, so 1. Newtonian fluid, so it matches with 3. In viscid fluid, again the viscosity is 0, so 1. And the real fluid has no non-zero value for viscosity, so option 2. Correct answer is A1, B3, C1, and D2. Next, the pressure inside a soap bubble of 50 mm diameter is 25 Newton per meter square above the atmospheric pressure. Then the surface tension of a soap film would be, the pressure and surface tension relation for soap bubble is P is equal to 8 sigma by D. So just find out the value of the surface tension. So just rearrange this formula. So sigma is equal to P D by 8. So value of P is 25 into 50 mm. So convert it into meter. 50 into 10 to the power minus 3 divided by 8. Okay, so if you calculate this, the value will come out to be 0.156 Newton meter. Okay, 0.156 Newton meter. Now next, so a Newtonian fluid is one which has a linear relationship between shear stress and rate of angular deformation. So option B is the correct answer. Next, unlike the viscosity of liquid, the viscosity of gases increases with the increasing temperature. This is due to the phenomenon of viscosity is because of cohesive and molecular momentum transfer. Okay. So for the liquid case, increase the temperature of liquid, so the bonding or cohesive forces will get decreases. So the viscosity of liquid decreases. But for the case of gaseous, as you heat up it, the molecular moment transfer increases. So the option B is the correct answer for this question. Okay. So the increase in momentum transfer in the molecules. Then next, a spherical water drop of 1 mm in diameter split up in air into 64 smaller drops of equal size. The surface tension coefficient of water in air is 0.073 Newton per meter. The work required in splitting of the drop is. So the work required for splitting up the drop is given as 4 pi sigma r square n raised to power 1 by 3 minus 1. This derivation I have explained in the theory lecture. So we have derived this end result for the work required for splitting of a bigger size droplet into small diameter droplets of n number. So value of n is here 64. So if you put the value in this equation, so 4 5 sigma, value of sigma is 0.073. The value of r is nothing but the bigger size water droplet. It is 1 meter mm in diameter. So just find out the its radius. So it is 0.5, convert it into meter, so into 10 raised to power minus 3. Inside a bracket n, there is 64 raised to power 1 by 3 minus 1. Okay, so just you simply find out this, the value is came out to be 0.69 into 10 raised to power 6 joule. 10 raised to power 6 joule. Option B is the correct answer. Next, 150 mm diameter shaft rotating at 1500 rpm within a 200 meter long journal bearing with 150.5 mm internal diameter. The uniform annular space between the shaft and the bearing is filled with the oil of dynamic viscosity 0.8 points. The shear stress on the shaft will be. So again, from the Newton's law of viscosity. So there are basically the three types on which the numerical may ask. I will explain the types of numericals could be asked on the basis of Newton's law of viscosity. So the first one is, just say this, the plate which is fixed, okay, and one more plate, okay, which is free to move, and these both the plate have filled with some viscous fluid, and now this upper plate is moving with velocity u. So this is one type. Now the second type is, say this is a horizontal surface. Now you have some inclined surface, okay, with the horizontal as a theta, and say this is the plate, okay, and between the inclined plate and this plate there is again some viscous fluid, okay, or a thin layer of viscous fluid, and this plate slides down over the inclined plate. This is the second type. Now the third type is a journal bearing. Okay, I have taken the cross section. in which a shaft is rotating. So here again, there is some viscous fluid. So this bearing has a diameter d, the shaft has a diameter small d, and to find out the thickness of thin oil film, okay, so means y. So the y could be calculated from d minus d divided by 2. So formula for shear stress is mu into du by dy. So now viscosity is given, which is 0.8 poise. Now how to find out the velocity? Okay, so velocity of shaft. So RPM is given. You can find out the velocity by formula pi d n by 60. And already I have told you that how to find out this one. Tau is equal to mu. Mu is 0.8. It is in poise. Now convert it into Newton second per meter square, means in SI unit. So just multiply with 10 raised to power minus 1 into pi d n by 60 into y. 1 means it is in divide. Okay, so into 1 by y. Value of y is d minus d divided by 2. So this is all in multiplication. Now if you solve this, the value of tau is come out to be 3.77 kilonewton per meter square. Okay, so option C is the correct answer. Now the plate weighting 150 newton. Okay, next question. A plate weighting 150 newton and measuring 0.8 meter by 0.8 meter just slide down the incline plane over the oil film of 1.2 mm thickness. So just you have given some inclined plane like this, and over which a plate is sliding down, and the inclined plane and plate has some oil film thickness which is 1.2 mm. The plate 8 into 0.8 meter. Okay, and the weight of the plate is 1 newton. So obviously the weight of plate will act in a downward direction. So W is equal to 150 newton. 150 newton. Now plate is sliding over the inclined plane, but the weight will act in the downward direction as I have shown in the arrow. So this angle is given theta 30 degree. So if you resolve this weight of the fluid in x and y direction, so this is resolution for the weight of fluid. So this angle theta will come out to be 30 degree. So this component of weight is F. It is, this angle is with the vertical. So it is F sine 30, and this component is F cos 30. So now we have to find out the viscosity. So to find out the viscosity, the basic formula is tau is equal to mu du by dy. Okay. Weight is given, so tau is nothing but F into area is equal to mu into du by dy. And this du by dy, all the time I have writing it is in gradient as or differential gradient. That means the initial velocity is actually 0, and dy is nothing but the difference, that is with the oil film thickness has how much height. Okay, that's it. So all the time it is not necessary to write du by dy, or simply you can write it as u by y. So F is given, so it is F, the horizon or in the direction of plate moving, the component of the weight is F sine 30 into area of the plate is 0.8 into 0.8 is equal to mu, that you have to find out. Value of u 0.2 meter per second divided by y is 1.2 into 10 raised to the power minus 3, and the value of F is nothing but 150. So this is the equation, and if you find out the value of mu, so that mu will come out to be 0.3 newton second per meter square. Okay, next, a flat plate 0.1 meter square area is pulled at a 30 centimeter per second relative to another plate located at a distance of 0.01 centimeter from it. The fluid separating between them being water with viscosity of 0.001 newton second per meter square, and the power required to maintain the velocity of the fluid. So I will just go back by 2 slides. So here I have explained you all the cases on which probably the numerical will ask in the examination. The first one is related to the plate. Okay, one is fixed and other is moving, and both the fluid are separating by the viscous fluid. The second case is on inclined plane, and third one is the shaft. Okay, the shaft is rotating inside the bearing. So the question that we are dealing with, it is based on the moving plate. Okay, that means one is fixed and other is moving. Both the fluid has some viscous fluid with viscosity, and some distance is also given between the two plates. So I will just explain you the formula. We can solve this numerical. So first formula is Newton's law of viscosity, that is tau is equal to mu. I will write it as a v by y, and other formula is p is equal to f into v. So you have to remember this formula. For power, p is equal to f into v. Now from this equation we can find out the force. So tau is nothing but force into area. Put the value of tau. So F into A is equal to mu into V by Y. Okay. So F is equal to mu into V by Y, okay, divided by A. So from this equation you will get the value of F. Put the value of F in this equation P. So P is equal to value of F is mu now into V divided by A into Y, and the remaining V. For power, the formula will become mu into V square by E into Y. If you put all the value in this equation, you will get the value of power. Okay, so the power value of power is 0.09 watts. When the pressure of a liquid is increased from 3 meganewton per meter square to 6 meganewton per meter square, its volume is decreased by 0.1%. The bulk modulus of elasticity of the liquid is. We have to find out the value of K, and the formula is change in pressure to volumetric strain. So here the volumetric strain actually is given directly. It is 0.1%. It is 0.1%. Change in pressure is also given. So just put the value. So K is equal to 6 minus 3, that is divided by 0.1%. If you solve this, it come out to be 6 minus 3 divided by 0.1 divided by 100. So this is the meaning of percentage. Okay. So if you solve this, so value will be 3. So difference 6 minus 3 is 3. So you can see this. So value will become 3 into 10 raised to power 9 Newton per meter square. Okay. So next, a liquid has a specific gravity of 0.9 and kinematic viscosity of 6 Stokes. What is the dynamic viscosity? So very simple. So formula of mu is rho into nu. Again, the viscosity is given 0.9. So into density of water, if you multiply it, you will get the density of that liquid into nu. The viscosity is again given in Stoke. It is 6 Stoke. Convert it into Newton second per meter square by multiplying 10 raised to power minus 4. So if you find out this value come out to be 11.14 Newton second per meter square. 11.14 Newton per meter square. Next, a flat plate of mass 1.5 into 10 raised to power 6 mm square is pulled with the speed of 0.4 meter per second relative to the other plate located at a distance of 0.15 mm from it. What is the power required to maintain this speed if the fluid separating them has a viscosity of 1 pi? So formula for P is F into V, okay? And this F is came from the Newton's law of viscosity, that is tau is equal to mu du by dy, and this tau is nothing but the force into area is equal to mu du by dy. So F come out to be mu by A into du by dy. If put this value in this equation, so you will get P is equal to mu by A into, and you can write this velocity gradient as a V by Y directly into V. So it is mu V square by AY. So if you put this value, so all the values are given. Velocity is given, viscosity is given, Y is given, area is also given. So it is come out to be 160 watt. Dimension of surface tension. So how to find out the dimension? Just I will give you the example. So the unit of surface tension is Newton per meter. Now convert that unit into the fundamental quantity. Okay, that is nothing but mass into acceleration. So this is formula for Newton. So mass is unit has kg, the acceleration has unit meter per second square. So put fundamental quantities for Newton. So here it comes out to be kg into meter divided by second square whole divided by this meter. So this meter will get cancelled. The unit is kg per second square. Okay. So the property from the properties dimensions are m to the power 1 and t to the power minus 2. So option D is the correct answer. Next, an incompressible fluid, kinematic viscosity is given, then specific gravity of the fluid is given equal to 0.88, is held between two parallel plates of the, if the top plate is moved with velocity of 0.5 meter per second, while the bottom one is held stationary. The fluid attains a linear velocity profile in the gap of 0.15 mm between this plate. The shear stress in Pascal on the surface of top plate is. So again, this numerical is based on the Newton's law, that is mu into V by Y, mu into V by Y. So directly here, the dynamic viscosity is not given. Kinematic viscosity and specific gravity is given. So you have to use rho into nu instead of mu. So formula will become tau is equal to rho into nu into V by Y. That's it. So how to find out the rho? The specific gravity is given 0.88. Just multiply it by 1000. You will get the value of density. Now value of nu, it is in meter square per second. Okay, already in SI unit. So just put all the values. So you will get the value 0.651. Now next, a journal bearing has a shaft diameter of 40 mm and a length of 40 mm. The shaft is rotating 20 radian per second and viscosity of the lubricant is 20 millipascal second. The clearance is 0.02 mm. The loss of torque due to the viscosity of the lubricant is approximately. Here in this question, the difference is only you have to find out the torque. Now how to find out? So we have a basic equation, that is tau is equal to mu into V by Y. And here directly the speed is given. So formula we have V is equal to R omega. This R is nothing but the radius of the shaft, and the speed is already given. So V is known now. Y is given, it is 0.02 mm. Okay, we have to just convert it into SI unit. It is given. Now the viscosity is given. The viscosity is 20 millipascal second. So all the quantities is given. From here we can find out easily the tau. So if you put all these value V, Y and mu in this equation, is force, it is nothing but area. Okay, area. From this equation you can find out the value of F. So F will become tau by A. We have to find out the torque. The formula of torque T is equal to F into D by 2. F into D by 2. So this D is nothing but again the shaft diameter. First we have to find out the torque by using this value. Then we have to find out the F force by using this relation. Once you know the force, so the torque is nothing but F into D by 2. So all the parameters you know now. So you will get the value of torque is 0.040 Newton meter. Now the difference in pressure across an air bubble of diameter 0.001 mm immersed in a water. So pressure difference means we have to find out the value of P, and P is equal to 8 sigma by D because it is air bubble. So 8 into sigma is 0.072 divided by diameter is 0.001. Okay, and if you solve this, you will get a value of 576. So this way we have completed the all the numericals and the theory questions that have been asked in the examination in a GATE and IES examination. So I have collected all the questions from the 1998 to 2022 for the IES, and for the GATE examination it is up to 2014, and till onwards in the GATE examination also same question has been asked with a little change in the value. So mostly we have seen that questions have been asked on the Newton's law of viscosity, then surface tension, and then capillary rise. Okay, and then types of fluid. So these 4 topics from the first unit of fluid mechanics is very important, and the questions you can see they are very easy. Within a minute you can get the answer if you have been clear with these properties of fluid and its classification. Okay, so hope you have gained something from this video. So if you like this video, so definitely don't forget to share and subscribe the channels. Thank you very much.